Hello, hello, hello.
You feel a little better? Hi, Dad.
Hi.
You have school tonight?
Yep. Hey, Joe.
Hey, Tom, how are you?
All right.
You don't want to watch the news?
Good evening, everyone. I hope you're all well.
How you doing?
Hanging in there, brother.
All right, it looks like it's post time here. Last week you took quiz number 1. I sent you the answers to the quiz. Does anybody have any questions about the quiz? I'll take that as a no. All right. Yeah, with the answers in your hand, you shouldn't have many questions. If anybody's unhappy with their results, I can give you an 800 number you can call. I'm sure they'll help you resolve any issues you might have.
So we can go to the full board.
Yeah, there you go. You can appeal that decision. I also sent you the answers to homework number 3. Did everybody get those?
I believe so.
So hopefully you'll be able to grasp that, not have any questions about any of the questions that were in homework number 3. Tonight, we got to start on physics and thermodynamics. And that always starts with a math review. All right. Math is a tough subject for most people because you don't do it anymore. All right. You did it in school because they made you. And now that you don't have to do it, you don't do it anymore. All right. The unfortunate thing is there are some math questions on the fireman's exam. There are math problems on every exam in this field. So I think everybody kind of gets that. So why don't we start with a little review tonight? If you've got the handout, You can follow along. But basically what this handout is, let me get this squared away here. Basically is just a reminder of stuff you already learned. Most of it you learned in grade school. All right. All right. Couple of things they're going to make you do is calculate square feet. All right. Or square footage of a tube. All right. 1 square foot, of course, is a box. 1 foot on each dimension, 12 inches or 144 square inches. All right. The area of a rectangle is the length times the width. Sure, everybody remembers that. The circumference of a circle, they'll ask you this question, is pi times the diameter. All right. For the purpose of the state exam, they're telling you to use 3.14 for pi. They tell you it's only necessary for you to calculate out to 2 decimal points for every math problem. All right, so you don't have to do anything more than that. They tell me we put people on the moon calculating out to 2 decimal points. So close enough for government work is probably an expression you heard. All right. The area of a circle will depend upon your age. Many of you learned it as pi r squared. All right. Does that ring a bell for anybody? Yeah. All right. That's how I learned it, because I went to parochial school. And when the nun told me pi's r square, I told her pi's are round, and she promptly hit me with a ruler. And I learned the main rule of going to Catholic school. Don't make any comments. But today they're teaching kids diameter squared times 0.7854. So you may have learned it that way. All right. The point is, it doesn't matter how you calculate the area of a circle. All right. You'll get the same results no matter how you do it. All right. Now, some of the information on this handout is for the higher level licenses. For instance, the next one, the area of a ring. All right. That's the question where they ask first and second engineers to calculate the area of an OG ring, which is used in the old vertical fire tube boilers. You won't need to know that, so you can cross that one off. All right, that's not coming your way. All right. There'll be a couple of questions on volume on the state exam. All right. A cubic foot, all right, is 3-dimensional, 1 foot on each dimension, or 1,728 cubic inches. If you want to find the volume of a rectangle, such as a room, you'll do the length times the width times the height. All right. The volume of a cylinder, such as a tank, all right, is the area of the base times the height. All right. Surface of a cylinder is not something they're going to ask you. That's if a problem they ask first and second engineers. How much paint would you need to buy if you were asked to paint a tank? So you need to find the surface area of a cylinder. All right. Now at the bottom of the page are the big ones. All right. These are the ones you got to remember. And again, hopefully many of you remember most of these anyway. 1 gallon of water occupies 231 cubic inches. All right. A gallon of water weighs 8.33 pounds. All right. A cubic foot of water is 7.5 gallons. And a cubic foot of water weighs 62.5 pounds. 62.48 to be specific. All right. That can be found by multiplying 7.5 times 8.33. All right. 1 pound of water occupies a space of about 0.016 cubic feet. All right. So these are something that you probably bumped up against somewhere in the past, but chose not to remember it for whatever reason. Okay. As far as atmospheric pressure, most of you know it as 14.7, close enough for government work. The actual number is 14.696 PSI. All right. Couple of things here. 1 foot of water column. That's a column of water, 1 foot tall, exerts a pressure at its base of 0.433 PSI. To get 1 pound of water at the base of a column of water, the column of water would have to be 2.31 feet tall. All right. Now, I want to illustrate that because this one comes up quite a bit on the state exam. All right. So what I just told you is this: a column of water, 1 foot tall, exerts a pressure at its base of 0.433 PSI. That's pounds per square inch. A column of water, 2.31 feet tall, exerts a pressure of 1 PSI at its base. If you know anything about mathematics, you probably figured this out, that this number, 2.31, is the reciprocal of this number. In other words, if you take 1 and you divide it by 0.433, guess what it's going to equal?
2.31.
2.31. All right. So these are all interchangeable. Does everybody get this? All right. One of the questions they're going to ask you is if this column of water, 2.31 feet tall, exerts 1 PSI at its base, how many inches is this?
2 1/3 inches is what you're saying.
Say it again.
2.31 inches is what you're saying.
No, I'm saying 2.31 feet is how
Oh.
many inches?
Oh, 12, 24 and a third.
Okay, good. If you're gonna multiply that by 12, all right, you'll get 27.72 inches of water column. All right. It is exactly the same as 2.31 feet. Does everybody get that? All right. Sometimes though, for pressures that are very slight, we use inches of water column. Has anybody ever heard of that? All right. For things like draft, gas pressure coming into your house, all right, the pressure is so low that a pressure gauge wouldn't measure it. It has to be measured in inches of water column. All right. But it's the exact same thing. All right. That means that each inch of water column represents a pressure of 0.036 PSI.
How wide is that column?
That's an excellent question. But here in the United States, long before you and I got here, what they decided that all pressure is going to be measured by the square inch. All right. So let's say I had a tank, and just to exaggerate this ridiculously, let's say it's 10 miles across. I want to know how much pressure is exerted by the water in it. All right. To measure pressure, I'm only looking at 1 square inch. Does everybody get that? All right. The total weight of the water is a completely different question. Does everybody also get that? All right. Here in the US, we measure pressure in pounds per square inch. All right. All right. So is everybody kind of good with this? All right. Now, one of the things I tried to talk to you about earlier was this. All right. Atmospheric pressure or absolute pressure, we measure with what type of device?
Barometer.
The barometer. The barometer measures pressure in inches of mercury. A standard atmospheric day, all right, is represented by 29.92 inches of mercury. That equals 14.696 PSI. All right. That means if you divide 14.696 by 29.92, you should come up with 0.491. Each inch of mercury equals 0.491 PSI. The reality is you hear this number every day, because what does barometric pressure affect for you and I?
The weather.
The weather. All right. If you were living around here this weekend, you knew that the barometer was high. The barometer this weekend was a little over 30 inches, about 30.2. And that means the nice weather we had stayed here. Guess what's happening right now? The barometer is falling. And what that means is we have a low pressure area where we live. And that means weather from somewhere else is coming here. That weather happens to be the hot weather that's out in the Midwest right now. All right. You probably saw the forecast for the next couple of days. It's going to get hot, right? All right. So that's how this whole thing works. All right. Now, as heavy as they're going to get into this with second fireman is that simple question. How do we measure atmospheric pressure, or how do we measure absolute pressure? And somebody already told me it's the barometer. All right. Any questions? All right. You've probably heard the term BTU, a British thermal unit. All right. A British thermal unit is equivalent to 778 foot-pounds of work. A kilowatt, again, a term I think you're all familiar with, is 1,000 watts. That is also equal to 1.34 horsepower. A megawatt is 1,000 kilowatts. A megawatt typically used in generating stations or people that buy large quantities of electricity. All right. A horsepower here in the United States is 33,000 foot-pounds per minute. That in itself is equivalent to 0.746 kilowatts. All right. A kilowatt hour can be produced with 3,413 BTUs. And a horsepower hour, what they call a mechanical horsepower hour, requires 2,544 BTUs. All right. For those of you that are in the generating business, that work in plants that generate electricity, all right, the heat rate is how they rank power plants. How many BTUs it takes them to produce electricity. Since there's a whole bunch of different ways of doing that with nuclear power, garbage, all right, coal, natural gas, all right, the calculation says this: if you take the total fuel input, that's the fuel that you burn in the boiler, and you divide it by the net electrical generation, it will tell you how many BTUs it takes for you to produce a kilowatt of electricity. All right. That's how they rank power plants, by how efficient they are. The more efficient plants come on first, the least efficient plants come on later. Does everybody kind of get that? It's a consumer-driven market, what they call a free market. So yeah, we want the lowest price possible. For third engineers, one of the things they're going to ask you is this: what is the linear coefficient of expansion of steel? All right. The most common substance that we use in this industry is carbon steel, good old American steel. And as I mentioned to you earlier, it has an annoying characteristic that when it gets hot, it expands, and when it cools, it contracts. The cool thing is it expands and contracts at a known rate. That rate is listed right here, 0.0000734 inches per degree of temperature rise. That coefficient of linear expansion is a number the third engineers should remember. Sometimes that's all they ask you. What is the linear coefficient of expansion? All right. If they want, they can also ask you the calculation. All right. The calculation looks at this. It says expansion is going to be equal to the length of the pipe times the coefficient of linear expansion times the delta T, the temperature differential, times 12. All right. And I know you probably really don't care, but to give you an idea, a 300-foot long steel pipe, this happens to be an alloy steel pipe, 300 feet long, will expand about almost 16 inches when it goes from ambient air temperature to its hot condition. Unless you plan for that, that could be problematic for you. All right. Now, this problem happens to come off a first and second engineer's exam. So, you're not going to get anything like that. But again, they ask third engineers one of two ways. They ask you either the formula, or they ask you what is the coefficient for carbon steel. All right. Specific heat of common substances, we'll talk about this tonight, but the only one you need to remember is the specific heat of water is 1, and the specific heat of air or flue gas is 0.24. That's how many BTUs it takes to raise 1 pound of that substance, 1 degree Fahrenheit. All right. The rest of this we'll cover as we move on. All right. But let's do this. Let's take a look at some of the math problems on the second fireman's state exam. In fact, this worksheet covers just about all the problems that are on the second fireman's exam. How many of you remember practicing how to convert Celsius to Fahrenheit or Fahrenheit to Celsius when you were in school? Nobody remembers that? No?
I was sick that day.
Yeah. I don't think it was one day. There was about 10 years where they try to convert this whole country to the metric system. They gave up. They realized we weren't really all that interested. All right. But the thing is this, for the second fireman's exam, they often make the problems very simple. For those of you that are looking at this problem number 1, what is 100 degrees Celsius?
212 Fahrenheit.
It's 212 degrees Fahrenheit. That's the boiling point on the Celsius scale. What's 32 degrees Fahrenheit to me and you?
0 degrees Celsius.
0 degrees Celsius is correct. It's the freezing point. All right. They often ask the real simple ones, so you don't even have to do any writing. All right. Any solving. All right. We'll talk about that in a minute. What pressure is exerted by a column of water 10 feet high?
Um,
4.3, 4.3 psi.
Very good. 4.3 psi. All right. That's perfect. All right. And that's a real problem because often in the DA, the water level is 10 feet above the center line of the pump. And that head pressure is found by multiplying 10 feet times 0.433 or dividing 10 feet by 2.31. You'll get the same answer either way. Does everybody kind of get that? What is the area of a 4-inch diameter circle? Don't all answer at once now. All right. For those of you that remember pi r squared, what's the radius of a circle 4 inches in diameter?
2.
2. 2 squared is what? 4 times pi is what?
12.52.
12.56. What?
Inches squared.
Square inches. Very good. 12.56 square inches. All right. What's the circumference of a 6-inch diameter circle? It would be what? 6 times pi, right? How about 18.84 inches, right? It's one-dimensional circumference. All right. Question 6 is on every second fireman's exam. How many cubic feet in a room with these dimensions? 10 feet long, 8.5 feet wide, with 7-foot ceilings. All right. How would you arrive at the answer?
10 times 8.5 times 7. So
10 times 8.5 times 7. 10 times 8.5 is 85. Times 7 is 595. What?
cubic feet.
Cubic feet. Very good. All right. Question 7 also appears on every second fireman's exam. You are expecting a fuel oil delivery of 6,800 gallons. Your fuel oil tank holds 10,000 gallons. What is the maximum amount of oil you can have in your tank? What don't you want to do to this oil tank? Yeah, you don't want to overflow it. So what's the maximum amount of oil that could be in the tank? Say it again. Oh, I put you all on mute because you were annoying me. Hold on.
3,200 gallons.
Very good. Now, if you know anything about fuel oil, especially number 6 heavy oil, what do they have to do to ship it? Anybody familiar with this at all? They have to heat it up. When you heat up fuel oil, what does that do to its volume?
Increase it?
Increases it. So on the state, they're going to give you a little bit, on the state exam, they're going to give you a little bit of margin to account for the fact that you have to heat up the fuel oil to pump it, transport it. All right. Does everybody understand? So the correct answer on the state exam is probably closer to 3,100 gallons. All right. To give you room to take the delivery. All right. You have a tank that holds 2,310,000 cubic inches. How much does the water weigh in that tank? What would be the step 1 of this math problem? Wouldn't it be to figure out how many gallons are in the tank?
Yeah.
Have you seen that number 231 anywhere tonight?
Yep.
What is it?
10,000 gallons.
It is 10,000 gallons. That is correct. All right. How much does 10,000 gallons of water weigh?
Times 8.3, whatever.
83,300.
83,300 pounds. Excellent. You see how simple this is? All right. All right. A 10,000 gallon tank is half filled with water. How much does the water weigh?
5,000 times 8.3.
41,650.
There you go. 41,650. All right. Very good.
Oh, he can do math pretty good in his head. I gotta write it down.
All right. Now you have to think about this one. A tank 10 feet long, 10 feet high, 10 feet deep, is filled with water at 62 degrees Fahrenheit. How much does the water weigh? So how much does the tank hold? All right, let me ask you this. What's the volume of the tank?
1,000 cubic feet.
1,000 cubic feet. Do we know anything about water? Like how many gallons in a cubic foot?
7.5.
7.5. So how much does this tank hold?
1,000 divided by 7.5. 700 and some odd.
How about 1,000 times 7.5? So there's how many gallons in the tank?
7,500 gallons.
7,500 gallons. How much does that weigh?
62,475.
There you go. All right. Or if you look at the next one, how much does a cubic foot of water weigh? It's on that front page in that bottom paragraph.
62.48 pounds.
Right. So if you multiply that by 1,000, wouldn't you get the answer?
Yep.
All right.
62,000. Yeah. 40, 180.
All right. When they ask you, what is the standard pressure? What are they asking for? You use it all the time. Atmospheric pressure.
Oh,
What is it?
14 point.
Yeah, we could say 14.7. That's close enough for us, right? All right. A standard day here in the United States is 60 degrees Fahrenheit at atmospheric pressure. All right. That's how they rank performance of any engine, gas turbine, based on a standard day. What device measures absolute pressure?
Barometer.
The barometer. Excellent. How many turns for a slow opening valve to be full open?
More than
More than
5.
five.
More than 5 full turns. What do they call the heat that's required to change a solid to a liquid and a liquid to a gas?
Solid to a liquid. What do we call the heat?
Yeah, that's called latent heat.
Yes,
You may have heard of that. All right. How many BTUs to turn 1 pound of water into steam? That's 970.3. 231 cubic inches is equal to how many gallons of water?
One
One.
gallon.
One US gallon. How many gallons in a cubic foot?
7.5.
7.5. Beautiful. All right. How many foot-pounds of work in 1 BTU?
778.
778. Excellent. Standard pressure is equal to how many inches of mercury?
29.29 inches of mercury.
29.92 inches of mercury is correct. A column of water 2.31 feet high exerts how much pressure at its base?
14.69.
1 PSI.
1 PSI, that's right.
All right, I'm going to send you these homework questions right now. I'm going to review them, hopefully with your help, on Wednesday. Everybody get that?
Got it.
Here they come. I'm also sending you out homework 4 so you can look ahead at those. All right. Let's take a look at the lesson. Hopefully you'll be able to master these math problems without too much trouble. Now, let's see. Jolene, you've taken the test. How was the math?
It's simple, but they word it. They purposely try to trip you up by wording it all weird.
Yeah, that's pretty accurate. Why wouldn't they, right?
Yeah.
Make it difficult.
I think
It's
I got
math.
half of them wrong. Yeah.
All right. So let's go through this and see what you know. At the beginning of this handout, all right, there's definitions for work, power, and torque. All right. I know you've all heard of all of them. All right. But they're not going to ask anybody here about these. The only exception is they'll ask a third engineer, how do we measure power in this country? All right. And the definition of power is at the rate of performing work. So power equals work divided by time. Here in the United States, horsepower is the standard by which we measure power. All right. All right. How many of you have heard of torque? Torque is important in this business because it applies to how much turning force a body acts on another. All right. These are usually math problems. They ask first and second engineers. So I'm not going to go over this with you, but if any of you is a motorhead, what is 5252? Does that ring a bell to anybody? Any of you guys, race car guys, build engines, screw around with cars? Apparently not. The 5252 is where horsepower and torque are equal to each other. All right. That's the RPM where horsepower and torque are equal. All right, let's talk about steam, which is the main aspect of this business. All right. All right, the temperature at which water boils depends entirely upon the pressure. All right. You guys have already given you a blurb on this. You already know that water boils at your house at what temperature?
212.
212 degrees Fahrenheit. It's always going to do that because for all practical purposes, where is your house?
A little bit above sea level, pretty much.
Yeah, at or close to sea level. All right. At atmospheric pressure, 14.7 psi, water will always boil at 212 degrees. If I take that same water and now put it in a boiler under pressure, let's say 100 psi, that water is going to boil at 327 degrees Fahrenheit. In fact, remember this, the higher the pressure, the higher the boiling point of water, right? And if you want to sound like an adult, we no longer call it the boiling point, we call it the saturation temperature, all right? So as the pressure increases, the saturation temperature increases. Now, here's the really cool thing. When you boil water at your house, the steam that comes off that water is 212 degrees. If that's true, then what do you think the temperature of the steam coming off this boiler is gonna be?
327.
327 degrees. All right. That steam, as well as this steam, are what we call saturated steam. All right. That is steam that's at exactly the same temperature as the water from which it was generated. All right. Put it this way, all boilers make steam at saturation temperature. Does that make sense?
Yep.
All right. Good. Steam can exist in 3 conditions. This is a question on the test. All right, steam can be wet, dry, or superheated. What do I mean when I say steam is wet?
Saturated?
Moisture.
Excellent. Who said that? Wet steam contains moisture, and it's always expressed as a percentage of moisture. For instance, steam with 5% moisture is what they call 95% quality steam. Just to make sure everybody gets that, if I had a boiler that was making steam with 3% moisture, what would be the quality?
97.
97%. If I had a boiler making steam that had no moisture, what would be the quality?
100%.
100%. 100% quality is what you and I would call dry, saturated steam. It contains no moisture, and as a result is 100% quality. To put things in perspective, fire tube boilers make steam about 95% quality. Water tube boilers make steam about 98% quality. Nobody makes steam at 100% quality. It's really kind of abstract, kind of theoretical. And the other type of steam is superheated steam. All right. If all boilers make saturated steam, then what would be a good definition for superheated steam?
The definition of superseded.
It's steam whose temperature is elevated above the saturation temperature. All right. How do we do that? We take that same steam, we pass it through some tubes that the hot flue gases pass over, and they give up their heat to elevate the temperature of this steam. If this steam is now 450 degrees, what I'm interested in is how much above the saturation temperature it is. All right. In this case, what is that?
123 degrees.
133 degrees.
Yeah, let's call it 123.
All
right. That's what's known as the degree of superheat. How many degrees above the saturation temperature the steam now is? All right. What's the advantage of superheated steam? It never contains any what?
Contaminant?
Moisture.
No, moisture.
All right. All the moisture's been evaporated. All right. It has more BTUs per pound. It can be transmitted longer distances before it condenses. All right. And I need less steam to perform a certain task. All right. So superheated steam, good. All right. Very good. Now, the temperature the definitions, I should say, of what they love are right here. The definition for saturated steam is dry steam at a temperature corresponding to its pressure. Superheated steam is steam at a temperature higher than that temperature corresponding to its pressure. All right. Now, the only other term I'd like to familiarize you with, I'm sure you've all heard of it, is enthalpy. Enthalpy always tells us the total heat content of a substance. All right. Enthalpy is always expressed as BTUs per pound. All right. Now, I know what you're saying. Why do we need a term like enthalpy? Well, look at this example right here. If I told you I boil water at the house, the water is 212 degrees, the steam is 212 degrees, and I asked you which one's hotter, what would your answer be?
Neither.
Right, they're at the same temperature. However, you'd probably be surprised to learn that the steam contains 1,150 BTUs per pound.
Wow.
The water contains 180 BTUs per pound.
Wow.
What has more heat value? The steam, obviously.
Yeah.
The steam has higher enthalpy, more BTUs per pound. All right. That's why I make steam, to get BTUs. All right. So that's why the term enthalpy is important in this business, because temperature doesn't cut it. That makes sense.
Yep.
Right. Because usually in every boiler, the steam is at exactly the same temperature as the water from which it was generated. The difference is the enthalpy. All right. So let's move on to some stuff you definitely learned in grade school. All right. And they asked this on the second fireman's exam. What are the three states of matter? Solid, liquid, and gas. All right. If you think about water, it can exist as a solid ice, as a liquid water, and as a gas steam. Steam doesn't actually obey the laws of a perfect gas. So it's what scientists call a vapor. But here's the interesting thing. Superheated steam does obey the laws of a perfect gas. Saturated steam really doesn't. All right. but they're gonna ask you this, and I think you'd be embarrassed if you forgot this, because they laid this on you in the third grade. All right, so they also start to ask you about energy, specifically potential energy and kinetic energy. I think you've all heard those terms. Potential energy is energy possessed by reason of position or deformation. Kinetic energy is energy possessed by reason of motion. All right. All energy on planet Earth is either potential or kinetic energy. All right. There are two laws of thermodynamics that apply to this business. The first and second law. The first law states that energy cannot be created or destroyed, but may be converted from one form to another. And everybody gets this. You burn gasoline in your car engine, all right? You didn't make the gasoline go bye-bye, all right? You just changed it into something else, exhaust gases, all right? The second law of thermodynamics says no machine, actual or ideal, can both continuously and completely transform heat into mechanical energy. The bottom line is this: nothing, no machine is 100% efficient, right? And that we know to be true. So, again, you might have known these all along. All right. On the next page, heat is energy caused by molecular activity. All right. It's important that you recognize that if they use the term internal energy or intrinsic energy, they're talking about that molecular activity. All right. Temperature is the degree or intensity of heat. All right. Heat is always transferred from a substance with a high temperature to a substance with a low temperature. All right. That's the way heat flows. And in boilers, this is especially true. There are three methods that heat is transferred: radiation, convection, and conduction. All right. On the next page, I give you a little blurb on each. Radiation is heat transferred by light waves without a material carrier. All right. For instance, you stepped outside today, you felt the sun on your face. You know, you probably recognize that the sun is 93 million miles away. All right. What you're feeling is the radiant heat from the sun. All right. Convection is heat transferred by currents in a fluid. All right. And conduction is heat transferred from molecule to molecule. Inside a boiler, all three of these things are taking place. All right. Now, in our discussion about superheaters, we talked about the radiant superheater and the convection superheater. Those devices are referred to that way because the radiant superheater receives the bulk of its heat through radiation. It's located directly in the fire and the direct line of sight with the fire. So it gets most of its heat through radiation. The convection superheater is in the back gas pass of the boiler. It doesn't see the fire, but the hot gas is flowing over it, how it gets its heat. So often in this industry, the way a device receives the majority of its heat is how we refer to it as. Hence the radiant and convection superheaters. Now to convert temperature, and I recommend you know how to do this. The state is pretty famous for stopping a tradition at any given moment in time. Now, I told you, when they ask you to convert Celsius to Fahrenheit or Fahrenheit to Celsius, it's typically commonly used numbers like the boiling point, the freezing point, but it doesn't have to be. So you should know how to convert. All right. So if you know the Fahrenheit temperature, you subtract 32 degrees from that, and then you divide it by 1.8, and that will give you the Celsius temperature. All right, if you know the Celsius, you can multiply it by 1.8, add 32, and that will equal the Fahrenheit temperature. All right. For years, the state asked second firemen to convert 22 degrees Celsius, 2 degrees Fahrenheit, or convert 105 degrees Fahrenheit to degrees Celsius. I showed you how to do these step by step on this worksheet. All right. I would recommend practicing a couple just so you remember how to do it. Depending on when you went to school, you probably learned this using the fractions 9/5 or 5/9. Does that ring a bell for anybody? That's because 9 degrees on the Fahrenheit scale is equal to 5 degrees on the Celsius scale. All right, that's why they had to use 9/5 or 5/9. Today, because every little kid has a calculator on their phone, all right, 9/5 is actually 1.8. So if you divide by 1.8 or multiply by 1.8, it's the same thing. All right. Now, just a word of caution here. Absolute temperature. The first license they ask about this is third engineer. All right. So second firemen don't really need to pay attention here, but the temperature scales, Fahrenheit and Celsius, were done for our convenience. Scientists, people that are interested in real science, deal in absolute temperatures. All right. And absolute temperature starts with absolute 0. All right. On the Fahrenheit scale, absolute 0 is minus 460. All right. So to find absolute temperature on the Fahrenheit scale, what they call degrees Rankine, you add 460 to the Fahrenheit temperature, and that will give you absolute temperature. On the Celsius scale, it's called degrees Kelvin, and you add 273 to the Celsius temperature to get degrees Kelvin. All right. Again, they're only going to ask third engineers about this, so I wouldn't worry about it if I was a second fireman candidate. One other fun fact that they might ask you about, does anybody remember at what temperature Fahrenheit and Celsius are exactly the same? It's minus 40 degrees. At minus 40, it's minus 40 Fahrenheit and minus 40 Celsius. All right, just another fun fact you'll learn here. I think everybody here knows what a thermometer is. A thermometer has a pretty limited range. but good enough for me and you. A mercury thermometer goes from about -40 to about 250. All right. And I think we all realize that if it gets hotter than 250, we're screwed anyway. All right. And I don't know what you're doing if you're outside at -40, but knock that stuff off and get in here. All right. All right. For really high temperatures, the device they use is a pyrometer. And that's the question they like to ask second firemen. What device or what does a pyrometer do? Pyrometers measure high temperatures. All right. For third engineers, they know you guys have been in plants for a while. All right. They're going to ask you, can you name 3 types of pyrometers? All right. The most common pyrometer out there today is a thermocouple. All right. I think many of you are familiar with thermocouples. They work in the -300 to about 3,000 degrees Fahrenheit range. All right. The radiation pyrometer, anything above 1,000. The optical pyrometer really has no limits. The Seeger cone pyrometer, up to 3,650 degrees. All of these devices help us determine furnace temperature. All right. That's what we're really interested. How hot is the fire in the boiler? All right. Typically, the average combustion temperature is around 2,700 degrees Fahrenheit. So we couldn't use a thermometer or measure that. At the bottom of the page, all right, is something everybody here seems to understand. The barometer is the device that we use to measure atmospheric pressure. All right. That's 14.7 PSI at sea level. It decreases about 1/2 pound for every 1,000 feet of elevation. All right. So has anybody heard of the term the Mile High City?
Yep,
Where is that?
Colorado.
Denver, Colorado. All right. They're at 5,000 feet. All right. Water boils. Does it boil at a lower temperature or a higher temperature?
I'd say a lower temperature.
That is correct. Water boils at 192 degrees there.
Wow.
So you can make your noodles really fast in Denver, Colorado. All right. Your ramen, whatever they call those things. All right. All right, there's a few definitions here that they're going to beat you up on. And this goes for all licenses. The definition of sensible heat and latent heat. Sensible heat is defined as the heat added to a substance that causes a change in temperature that can be measured with a thermometer. Think about it. To me and you, all heat should be sensible. If we add heat to something, we expect that substance's temperature to change, right? Sensible heat. All right. However, latent heat is heat that we add to a substance that causes a change of state without a change in temperature. All right. Water has 2 significant places, temperatures, I guess, where latent heat occurs. All right. At 32 degrees Fahrenheit, we can have ice or we can have water. If we took 1 pound of ice at 32 and we add 144 BTUs of heat, will have a pound of water at 32 degrees Fahrenheit. A change of state, but no change in temperature. The same thing happens, all right, at 212 degrees Fahrenheit. I can have a pound of water at 212, but if I add 970 BTUs of heat, that pound of water will become a pound of steam at 212 degrees. All right. So at the freezing point, the heat that we add there is known as the latent heat of fusion. All right. At the boiling point, it's known as the latent heat of evaporation. Many substances have a latent heat of fusion and a latent heat of evaporation. We just don't care about them. The only thing you and I are interested in is water. That's how we make steam. All right. Any questions? So they're going to ask you on the state exam the definition of sensible heat, latent heat, and they're going to ask you, where does the latent heat of fusion occur? And where does the latent heat of evaporation occur? So you can be all around that. All right, the next page, British thermal unit, or a BTU. I'm sure everybody's heard that. The definition of a British thermal unit is the amount of heat required to raise the temperature of 1 pound of water, 1 degree Fahrenheit. All right. And I'll explain that in a lot more detail a little bit later. The second definition is specific heat. And you have to read this very closely because specific heat is defined as the amount of heat required to raise the temperature of 1 pound of any substance, 1 degree Fahrenheit. All right. As a result, the specific heat of water is 1. All right. And that's the reference point that we use. All right. You'll find out as we move on from here that water is the universal standard. And we use it as the basis for everything, mainly because it's consistent. All right. It weighs the same thing regardless of its temperature. All right. Does everybody kind of get that? So even though its temperature will vary a few degrees, right? Its specific gravity, its weight, all that stuff doesn't really change. All right. So specific heat is used to tell us how many BTUs it takes to raise 1 pound of any substance, 1 degree Fahrenheit. All right. His buddy's specific gravity is the weight of any substance when compared to water. All right. Now, this is important, especially if you're a third engineer. All right. This applies mainly to fuel oil, but also motor oils. All right. We made a rule in this country a long time ago that any fuel oil that we transport on a public way has to have a specific gravity less than 1. Can anybody tell me why?
Floats on water.
Excellent. All right. If we spill oil, where will it be? It'll float on water. It's lighter than water. All right. So fuel oil typically has a specific gravity less than 1. If I told you that I had a particular fuel oil and its specific gravity was 0.85. Could you tell me how much 1 gallon of that weighed? Remember, what's it being compared to?
Weight of water.
Do we know what a gallon of water weighs?
Yes.
So if I multiply a gallon of water, the weight of a gallon of water by the specific gravity, I'll get the weight of that fuel oil per gallon. Does that make sense? Is that what I get? Is that what you get? Everybody good? Yes, no, everybody understand this? All right. Sometimes they'll do this. They'll tell you gasoline that you put in your car weighs 6.7 pounds per gallon. What is its specific gravity? How would you go about solving that?
Divided by 8.33.
There you go. Divide 6.67 by 8.33. What would you get there?
0.8.
0.81.
Yep, 0.8. The specific gravity of gasoline is around 0.8, 0.80. That's how they ask that question for third engineers. All right, they're not going to beat up second firemen on this. Any questions? All right. All right, here's the money question. Specific gravity, you'll notice it tells us that specific gravity of water is 1 at 39.2 degrees. It's point of maximum density. All right. Why is water its most dense at that temperature? You people don't go outside much, do you? Right? Water is one of the few substances on this planet that when it goes from a liquid to a solid, it actually becomes less dense. The solid form of water is ice, and ice floats on water. Nobody ever noticed that before? Did you ever make a cocktail and put ice in it? You guys just beer drinkers or what? All right, one other thing about specific gravity. All right. Specific gravity, the reciprocal of specific gravity is density. All right. So just remember this, specific gravity, all right, is how many pounds a cubic foot of that substance weighs. All right. The density of of that substance is the reciprocal of that. All right. Or how much space 1 pound of that substance occupies. Does that make sense? Let me put it this way. If you know the specific gravity and you take the reciprocal of it, you divide it into 1, that will equal the density of that substance. That makes sense? I guess not, huh?
Mm-mm.
The last thing we'll talk about, we'll take a break, is specific volume. All right. All right. Now, the definition of this isn't important. All right. It's the volume of any substance when compared to an equal volume of water. What's important about specific volume is how it relates to steam. As steam pressure increases, the specific volume of a pound of steam decreases. All right. The higher the pressure, the less space a pound of steam occupies. All right. When you get up to the critical pressure, about 3,206 PSI, a pound of steam is about the size of a $50. All right. Specific volume is cubic feet per pound. How much space 1 pound of that occupies. Any questions about any of these? All right, why don't we take a 10-minute break here? All right. And I'll see you at 7:30. Hey, did you guys get that email I sent out?
Yep.
Yeah, I got
Okay, good. Very good. I'll see you in about 10 minutes.
Hey, Don. Yep. Yeah, because he's supposed to be coming down tomorrow. Those pots should have been here today. If you don't find them, send him an email telling him that they didn't arrive. All right? Thank you. Bye-bye.
Dad. Is the dishwasher ready to be put in? What? Is the dishwasher clean or not? Yes. Oh, well, I have to wait till Dad's done. Oh.
Going back on now.
All right, then I'm gonna leave to do that.
All right, looks like we're back at it here. No questions up till now, huh? Any questions on any of this stuff? Now, the only thing that'll come up about specific volume, all right, there's only one place that you can find the specific volume of steam. That's on a document that's pretty famous in this business, known as the steam tables. All right. The steam tables will tell you for every single pressure, the specific volume of steam. All right. So the question on the state exam is, where would you find information regarding the specific volume of steam? And you'll find that in the steam tables. All right. If you're going for your third engineers, they gave you a copy of the steam tables. Did everybody get that that's going for their third? All right. So we'll talk about that later on with you guys, but that's where you find information about specific volume. Is that right? So those are the definitions that'll come up on the state exam. So on the next page is a couple of things that you got to know. All right. One of them is important in this business. It's known as the critical pressure of steam. All right. And what makes that particular pressure 3,206.2 PSIA special is this. At that pressure, water becomes steam without the addition of latent heat. Right? And if you can't wrap your arms around this, try that. If you can't get your arms around that, try this. Water and steam have the same density at that pressure. They are essentially the same substance. All right. But the key thing is boilers that operate at or above that pressure are known as supercritical boilers. And they were said to be more efficient because they don't require any latent heat to change water into steam. All right. The temperature that corresponds to that pressure, the saturation temperature, is 705.4 degrees Fahrenheit. That's as hot as we can make water here on planet Earth and still have it remain water. All right. So at that pressure, the critical pressure, I can get water up to 705.4 degrees Fahrenheit. All right. That's the highest saturation temperature here on Earth. All right. That's the significance of that. All right. Now, the critical pressure, they're going to ask you, name two things that are special about it. All right. At that pressure, water and steam have exactly the same density. And latent heat is 0. So water becomes steam at that pressure without any additional heat. Any questions? Every now and then they'll ask third engineers, how many atmospheric pressures is the critical pressure of steam? And what they're asking you, how many times can you divide that by 14.7? All right, that's the equivalent of 218 atmospheres. And then one of the math problems they give third engineers is, what is the critical temperature of steam on both the Fahrenheit and the Celsius scale? So it's an exercise in converting Fahrenheit to Celsius. All right, they kill 2 birds with 1 stone there. All right. The next definition right below that is the absolute temperature or absolute zero of temperature. All right. Let's talk about absolute zero first. All right. At that temperature, there is no molecular motion. That means there's no heat. A perfect gas has 0 volume, and something known as entropy is equal to 0. All right. Now, the absolute zero of temperature is an interesting story. The guy who figured that out died in 1800. All right. And what he did, he took a volume of gas at a specific temperature, and he decreased its temperature by 1 degree Fahrenheit. And what he noticed is that its volume decreased by 1/491st, whatever that number is. And what he postulated was this: that would put the absolute zero of temperature 491 degrees below the freezing point, or roughly minus 460 degrees. In 1960, a couple hundred years later, we went into space the first time. And guess what the temperature in space was? Minus 460. So this guy, Avogadro was his name, nailed it. All right. All right. He hit it exactly right. The temperature is actually minus 459.6. That's the temperature of space. There is no molecular motion. There's no heat. A perfect gas has 0 volume. It's a vacuum in space. All right. And entropy, which is a measure of BTUs unavailable for work, is 0. So that's the absolute zero of temperature. Now, every now and then they have that question in the database. What 3 things make up the absolute zero of temperature? No molecular motion, perfect gas has 0 volume, and entropy is equal to 0. All right. Absolute zero of pressure should be pretty easy to understand. All right. It's a perfect vacuum, space. All right. We can't get a perfect vacuum on space, mainly because the machines that create a vacuum vacuum pumps, all right, aren't 100% efficient. So if we have to do an experiment that requires a perfect vacuum, we have to send it up on a spaceship to the space station where they'll do their little experiment. All right. Any questions? All right, now, one last thing, and I'll let you go for tonight. This is where I broke it up with the day class. The specific heat of common substances, all right? This number represents how many BTUs it takes to raise 1 pound of that substance 1 degree Fahrenheit. So the specific heat of water is 1. The specific heat of air is 0.24. All right. So you should recognize that immediately, that it takes 4 times as much heat to raise a pound of water as it does a pound of air. All right. Flue gas is exactly the same as air, 0.24. All right. Does anybody have any idea at all why hydrogen is on this list? All right, in the electrical generation business, the most common cooling medium for electrical generators is hydrogen. The reason for that, despite the fact that it's flammable and explosive, is that it has a very high specific heat. It will absorb 13 times as much heat as air before its own temperature starts to increase. Right? So it's used as the cooling medium in electrical generators, right? Hydrogen cooled generators. Right? Just a fun fact, they're not going to beat you up on that. All right. But that's where I broke it up for the day class. So we'll stop here. Look over that homework. We'll finish this up on Wednesday, and homework 4 will be due on Monday. I'd like to go over those math problems that I sent you tonight on Wednesday to make sure everybody kind of gets it. All right. Doesn't look too difficult, does it? Any of that math? So you should be good to rock and roll. Any other questions for me? All right, then I'll see you on Wednesday night. All right.
Thank you.
All right.
Thank you.
All right. Good night.